All right. Well, welcome everyone to a special Berkeley Seminar. We have Mike Dodds coming to talk to us from Galois. He's going to tell us a practical story about formal methods.
Imagine that, a practical story about formal methods. I'm Mike Dodds. Here's a bit of context on me. I used to be a professor in the UK. I actually, way back when, worked on graph transformation. So I do know what a push-out is, broadly speaking. I was not a very good kind of category theorist, which is why I didn't keep on working on it. And I also worked on things like separation logic and concurrency verification, relaxed memory. And since 2017, I worked at Galois as a principal scientist, lots of industry, government things, and I'm actually in the Bay Area working at Constellation as a visiting fellow until the end of December. So in recent years, I've become much more interested in AI safety and formal methods and whether we could use the formal methods for AI safety purposes. So probably everybody has heard of Galois at least a little bit, but I think sometimes we're a little bit mysterious from the outside. It's like, what is this thing, right? Okay. Well, in some ways, we're quite boring. It's like we're just a company that will sell you researchers by the hour. So we're sort of a temp agency, really. If you, well, really the government, wants to hire us to do research projects, often which are things like, hey, there was this paper, could we build a prototype? There's this prototype, could we build a better prototype? Could we sort of solve some problem? You can hire us to do that. And we tend to focus on security and reliability, so things like formal methods, crypto, things like this. And we work for DARPA a lot. Some commercial stuff. We've done a lot of work with Amazon Web Services over the years. So I think a lot of and I think if you look around the kind of Galois organization, you'll find a lot of people who have some sympathy for category theory as an idea, but it's also a lot of other math ideas that end up translating into practice. So I think that this talk, which is a bit of a it's one I've given before in various forms. I think the context here is that I joined Galois and I was like, you know what, I'm going to do some research, right? But what I actually ended up finding is that you've got to find people to pay for the research, and that means you get on calls with people to see whether they want to pay for things. And these are sales calls, so I ended up on a lot of sales calls. So I would have these kinds of conversations. People would say, hey, I've heard of formal methods and I'd like to do a formal method. And I would say, great, tell me about what you want. And then, what's your objectives, your target system, your team and your budget and things. And then sometimes it goes well. Mostly this doesn't happen, but 90% of the time we don't get things funded. But we scope things and the client is happy and everyone high fives, and then we keep on trucking. Then sometimes we can't fund what the client find a project the client wants, and then we all go our happy ways, and then they do other things with the money. And so I think that this is a pretty interesting thing to be doing, because as a professor, I never did this kind of thing, really. I never went along to the people I was allegedly helping and tried to sell them on the idea they should put their money on the line, doing the thing that they really wanted. I did that for government funding agencies, but not really other things. And so this talk is things I learned in 7 years of sales calls, right? I did a lot of this, and now I learned some stuff. I have some hot takes, and now you will get to hear some of my hot takes. So it's entirely a hot takes talk.
Quick question.
Oh yeah, go ahead.
Quick question. Are you happy to have left an academic position?
Yeah, yes.
Okay.
Yes. I recommend quitting academia. No, that's not true. It's
Well, we already all did.
No, I will say, just on theme for this talk, I think that having clients is initially very annoying, because you say, you want this, and they say, no, we don't. And then you think, oh, I didn't understand the world. But that's actually quite a good discipline for sharpening your intuitions. And so I feel like I've been, I don't know, not smarter, but I think that I have a more accurate and calibrated world model, because from trying to sell things to people. And so that's been the big advantage of it, is I actually have to make people happy rather than just making myself happy. Ultimately, it made me happier as well. Okay, so this is Baby's first economic model. You know, when you do projects, things cost things, they give you benefits. There are some projects that cost too much. There are things that actually make sense. And then we want to kind of figure out where those things are. So you think about cost, you think about holistic cost. You can use the word utility. We are in the Bay Area if you like, but cost is a perfectly fine word. Sorry, you should think about utility for benefits. So you can think of this as kind of a utility curve, I suppose. And I think that you have some break-even line. Most people have a point at which, you would do things, you do this thing rather than that thing. Everyone's sort of you want to go get a sandwich, you want to go get a piece of pizza, right? Which of these is the better one. You make some trade-off between them. And I think that this is maybe the most controversial thing I'm going to say in this talk. Engineering teams are somewhat rational. If there's something that's expensive and doesn't have benefits and something that's cheap and has a lot of benefits, they will probably, in the aggregate across the landscape of the world, the things that are cheap will end up being done more. That's kind of people aren't perfectly rational, but mostly people make those trade-offs, right? So an interesting question is when we're doing formal methods, lots of formal methods projects seem to live in this sort of region of doom down here where they are too expensive to get funded for the cost, for the benefit that they deliver. So this is sort of interesting because often I think as a researcher, we sort of talk about possible versus impossible. So you say, okay, is it possible to do this? Well, lots of things are possible, but a lot of things just possible but just don't pencil out. They just don't make sense in terms of the trade-offs. And it feels like a lot of formal methods tools projects live in this kind of region where they just don't make sense. So why is this? What's going on here? What could we do about it? So this is where we get to the kind of hot takes. So I've got a few hot takes. I will go through all of these in turn and then review at the end. The first hot take is these are also in some sense my job here is to say completely obvious things and hopefully annoy everyone in the process, right? So I'm going to attempt to do this. So one thing is doing things that are quick obviously sometimes beats being correct, right? So here's a cost-benefit curve that you probably don't want. You spend a lot of time doing kind of work and then you don't get much benefit. At the end, you get lots of benefit, right? This is kind of a thing that we probably don't want. Unfortunately, it's what the formal methods projects often look like. You do a lot of work setting up initial definitions. Maybe you even have to learn a brand new tool. Oh my God. And then you prove some lemmas and then you don't get any benefit at all. And then at the end, you prove the main theorem and you kind of celebrate. And this is very nice. The problem is that this doesn't really work very well when you're trying to sell things. Because what happens is that you go along to the client and they say, I know formal methods. I'd love some formal methods. And you sort of say, okay, so proof sounds amazing. What if we gave you this amount of dollars, sort of Y dollars, right? And then I go back and I sort of look at how this pencils out, and then it's just this tiny little region at the start here, right? And then you sort of come back to them and you say, how about you give us 4 times as much money, and so 4 times as much time and 8 times as much money, and then they don't call you back. They're like, well, we just can't afford that because they don't trust you, they don't know what they're going to get, and so it's really hard to kind of get persuade people to kind of do a 4-year kind of moonshot mission for when what they have sign-off authority for is $100,000 or something. So ideally, you would have tools that look like this, where you do a small amount of work and you get some benefits, and you do a small amount more work and you do a small amount more benefits. The good thing about doing projects this way is that you can do project 1, you can call the client and say, hey, wasn't that great? How about you give me some more money? And then they can do a bigger project 2, and then everyone is happy. Unfortunately, the formal methods tools are typically not shaped this way, and this makes life very difficult and annoying.
One other quick question.
Oh yeah, go ahead.
By formal methods, do you mean more than proving algorithms correct?
I think that, I should say that by formal methods, I mean automated proof, I mean property-based testing, I mean sort of all sorts of broadly proof, theorem-proving sort of technologies, including kinds of other kinds of fancy math that don't quite fit into that, model-based design, things like that. So the big question is why those are so difficult to kind of shape. So if you're a formal methods person, if you hang around at Galois long enough, someone will eventually say something rude about testing. And so they'll say, oh, but the problem is it's random, you can't find the bugs, you don't know if all the bugs have gone. But the nice thing about writing, like a very typical way to build software is you do some work, you run some tests, you find a bug, and then you do some more work and you do some more tests and you find some more bugs. And so you have this nice cost-benefit curve where like early on you find a bunch of bugs and then you fix them. And then you're like, oh, look, benefit, great, amazing. And so there's like a low early cost to improve correctness, but it's hard to get to high levels of correctness. But still, like this is what people seem to want, Like there's a reason that Python is popular. Another like super hot take, like a reason why people find it hard to scope formal methods projects is that cheap things beat expensive things. So so when we're kind of going around going, oh, well, wouldn't it be great if we formally verified everything? Like, I don't know if you've looked at any software recently, like a lot of software just doesn't have test cases, right? Which is like a lot of software doesn't have any documentation at all, right? And so there's a sort of hierarchy of kind of like levels of kind of correctness. And if you sort of, things you could do to make the software better. So if we start with like code review and testing and CI/CD, these things really work and they're not very expensive. And you can do more things. You can go down to fuzzing and modeling and model checking, and then go all the way to proof and correct by construction. But like the things high up this hierarchy are like incredibly effective, right? And they really, really work. I've been sort of using just seeing, even working with an AI, that you can kind of setting up like a sort of CI process, so you have a test suite, is very good at getting it to like not make mistakes. And the problem is like many systems don't even do this stuff, right? And so often you're sort of coming along and saying like, hey, you know what? You should do like a proof for this thing. And they're like, well, but is that good advice? Is it? So like you can end up in this sort of like strange world where you go to a client and they say, I'm interested in formal methods, and you review their code and you say, what about you wrote a test case? How about that? Would that be good? And they're like, yeah, no, that would be good. And then, well, it's hard to kind of come along and say, you need like your fully, sort of proven kind of, whatever. If you haven't like done any testing at all, probably your proof is not going to work at that point. It's probably sort of good to do cheap things before you do expensive things, because the cheap things are more predictable and they're also easier to staff, lots of other reasons.
So you also think the error bars on the benefit are probably usually bigger on the expensive one?
I think that's probably true as well, because they're typically more research oriented, and it's, there's just the tools are less mature or things like this. It's also like staffing is harder because you need to find somebody who can write lean, things like this. So yeah, it's like lower risk in general. There's a couple of things people try and do to sort of sell this. So like in practice, a lot of formal methods deployments look a lot like gold plating, right? So you sort of say, okay, well, you did all the testing, you did all the CI/CD, let's all do like all the kind of, let's do this, and let's do proofs at the end, right? Great. But the problem is that like this is only really makes sense for like someone who's done all the other things in the hierarchy, right? So you are sort of selecting out the vast, vast, vast majority of people, even in sort of high assurance world. So you're selecting out people who have done, I don't know, like kind of, you're selecting out like the vast majority of people building like cyber physical systems, even in things like high consequence domains. So the other thing you could do is you could sort of claim, very boldly that formal methods means you don't need to do any testing anymore. Guys, it's great. But the problem is like, this isn't really true mostly, because, well, mostly people don't trust formal methods tools enough to kind of replace existing techniques. And also like testing is kind of quite useful because you're testing it on the real system. And so it's really hard to kind of come along and say, I want you to just sort of like get rid of your test suites. We're just going to do proofs now. And so that means you kind of have to do the testing as well, which means you don't kind of get the benefits of it. Okay. The other, another super hot take that really kind of gets in the way is like correctness doesn't matter that much, right? Like, this is also like a slightly mind-boggling thing to me in being from a Galois point of view. So I think I had this kind of view of the world. I think that you sort of say, oh, like the software is also incredibly rubbish and sort of doesn't work all the time. And what if we could have like everything being correct, right? Well, this would be very good, but it turns out the revealed preference of people building software is they don't care that much about correctness. So I don't want to be too much of a troll about this. like obviously at some margin, correctness does matter. If your Python script literally does not do the thing you want it to do, then it does matter that it's like that it's not correct. But like for a lot of systems out there, the marginal value of like fewer bugs is 0, really. Like if they made it half, they removed a lot of the bugs, it wouldn't make them any better off because they wouldn't sell any more units. They wouldn't kind of like, they wouldn't have to do less testing because it's sort of like priced in some sense. And that's even true to my surprise, when I'm talking about things like, cars or, planes or, sort of weapon systems or whatever. Often, like the marginal value of making them less buggy is like not that massive, really. So like, especially this is true where there are trade-offs, cost-benefit trade-offs between correctness and other things that the team cares about. So if it means that you can't ship features, or you can't hire developers, or you can't staff the team, or you can't pay down technical debt because you're using some of the budget to pay for like correctness technologies, that means that you can't, you have a hard trade-off between something that will sell more units of the thing or kind of make your customers happier, and something where the benefits are just very sort of like nebulous to the team often. So like it's very important to figure out like why do they care about like using the tool? Like what's the thing that actually would make them better off? So here's an anecdote which I sort of blew my mind slightly. So we had a call with like it's like a medium-sized kind of contractor for Department of Defense like systems that build stuff where we really would like it to be correct because otherwise very bad things would in very obvious ways happen. And we sort of said, oh, well, suppose we made this like more reliable and secure, like without very much cost to you, would that be valuable to your business? And they said, well, no, it would not be valuable to us. We wouldn't care. We wouldn't care. I don't think they're like, we would stop you, but they were not enthusiastic about this. So, in my mind, what's going on? Well, their current reliability and security process works for them. They think they're already more reliable and secure than their competitors. Being more reliable and secure will not sell them more units. And it would mean kind of learning new tools. It would mean more technical risk in their stack. It would not kind of like make a difference to them. Go ahead.
Just curious about the titles. It says doesn't matter. Have you updated that it doesn't matter, or have you realized that they're wrong and their priorities are wrong, but you compromise? Oh, right, I was wrong, as you were saying earlier.
This means matter for sales, right? It doesn't mean to matter for morality or something.
I mean, yeah, I think that does the correctness of software matter, in a sort of cosmic kind of platonic way? I think it sort of depends on, I don't know. I'm sort of quite pragmatic about this. I think it does it matter for the team that you're trying to ask to use a tool that might help them? I think that's what I'm trying to say, is that for the teams that you're trying to give tools to, they often don't feel like it matters very much. And it might, this is like, the other thing to say is this is like, I think that once you're in the world of trade-offs, this isn't like some crazy cognitive distortion. This is like a legitimate perspective which comes from a totally reasonable utility function, which comes down to saying that there are trade-offs here between doing the thing that you want to do, namely use formal methods, versus like other things that would actually make their upstream customers happier. It might even be like better in like some global sense. So, if you can ship security fixes more quickly, that might be better for correctness than doing a fancy proof. So, like the kicker with this conversation with the DoD person was like, hey, what if we can make your compliance processes cheaper? So compliance is very interesting. So, when you ship a thing that flies or drives around or whatever, then you have to do these kind of really fancy compliance processes, which are sort of nominally about making the software more secure and reliable. In practice, they're often very process-oriented, and so they're very expensive. And so we said, oh, hey, what if we could make the regulatory compliance cheaper? And they were like, yeah, that would save us, some ridiculous number of millions of dollars a year, right? Okay. So these are sort of interestingly different things. Like what I was saying the first time around was like, could I increase the kind of security and reliability of the underlying object, the true level of reliability? They didn't seem to care very much. Could we make it so that they can certify this thing to be reliable and secure according to the process, which is very expensive, more quickly, well, in that case, they care very much. And without compliance testing, they can't sell the products. The compliance testing is very expensive. It's highly manual. The team hates doing it. It's hard to staff. It's just writing loads and loads of test cases. And it slows down release schedules. It reduces flexibility. It's grinding for the engineers, all this kind of stuff. So it's bad in general. And so the trade-off here is they're trying to ship products and they want to kind of do stuff. And if you can help them with a thing that costs them money or is good for the business, then they can actually use it. Okay. So another problem that you have trying to use formal tools, like if you're trying to prove things or test things, is that specifications mostly don't exist, or at least they don't exist in a form that formal methods tools can use. We're all mathematicians really. Ideally, what we have is definitions of the behavior of a system, which are mathematically nice and clean. They're stable over time, everyone agrees on them, and they're easy to reason about, and expressed in some fancy semantics using categories or whatever. This is a very nice world to live in, and I enjoy it very much. Regrettably, this is not common, but there are really things that have some of this structure. So if you think about things like cryptographic algorithms, or operating systems, or compilers, or cloud services, or hardware, they often really do have this kind of shape where you have a very nice clean description of the thing. The thing is very cleanly encapsulated. There's a nice standards document somewhere that you can write down. You really, really, really care about the thing doing what the standards document claims. And also, in the sense that there are very bad things that will happen otherwise. And these are all, so this is good if you can get it.
So these are the long-term systems, the things that last for decades or centuries or something, you could imagine that more like on the decade time scale. Is that kind of the idea that software or things that you expect to be in operation for decades, you would care about or they're more likely to be formalizable or something?
I think that's definitely part of it. I think another thing is having a really clean boundary, because you sort of, for example, an operating system might change a lot, but the API for the operating system might be relatively stable. And that means there's a sort of inside-outside distinction that makes it relatively easier to kind of specify.
Yeah, okay.
You don't have enterprise databases sitting here, which some of them are 75 years old. But this is not a good example of formal method successes. I'm not really honestly sure.
Well, I think databases are very interesting because you're right, they have sort of an interface, but also I don't think that there's a formally verified serious database out there. And I would guess that part of the problem, having looked a little bit at kind of database semantics, part of the problem is that the semantics is surprisingly fuzzy, and they often made trade-offs that make the actual behavior sort of faster by trading off kind of correctness, right? And I think the other thing that makes it tricky is that I think that there's not as clean an abstraction between the database and the application as you would probably need to kind of make that possible. And the systems themselves are just kind of unbelievably gnarly in terms of how they're built. And so that means, makes verification harder. But I think a database could be a good candidate as well. Like a cloud service from a certain point of view is a fancy kind of another kind of database. It's just that the cloud service, the difference is I think that Amazon's cloud service is sort of providing an API that they do really want to stay stable because they have a lot of legacy customers, whereas a database is sort of often more entangled with the logic of the application. But it's interesting. Yeah, that's a good question. Where is the sort of formally verified database? I don't know.
So how accurate is it to say the stuff that's more mathematizable is the stuff that's more stable?
I think that's another big bit of it. Yeah, I think that's close. I think these are sort of some of the candidate sort of properties. I think there are just some things which have nice mathematical properties inherently. I think stability really helps. I think user agreement or agreement by stakeholders really helps, and that's not, there's other bits of there's some bits of the OS where, they're just sort of, it's just tricky because they don't seem to have like a kind of clean interface that everyone agrees on, And there's sort of some other property which is like, how easy is it to reason about? And again, that sort of feels like it's, sometimes you get lucky, sometimes you don't. I think hardware abstractions are sometimes more difficult to reason about than like crypto, for example. I think crypto is a nice case. Like block ciphers are easier because they're just nicely shaped for kind of reasoning for various reasons. Anyway, yeah, so we'd like that to be true, right? So anyway, I mean, the point, I suppose, is like, these are all very nice things to have. We have all these verified things. The world is it's very unusual to have these properties of a real system. Most things aren't like this. And in fact, in practice, we have non-formalizable things, which are full of like total nonsense that we really don't want to have. Like, often we have like prose standards and RFCs and papers. These are fine. If you hang around the DoD, Department of Defense, long enough, what you find is that they love to use PowerPoint for things. And so they use PowerPoint for defining specifications, or like diagrams in PowerPoint decks. Lots of other stuff like code and reference implementations and code comments and test cases. In practice, the test suite is often the only spec that exists. So there's like all sorts of other stuff, like, tacit knowledge that everybody knows, but no one ever writes down, all this kind of stuff, right? And like everything is sort of, everything except these very narrowly scoped things are like this a bit.
Yeah, I've been noodling on this question for a minute, trying to figure out the right time in the presentation to ask it. This seems like the right one, but all of these tools are kind of like informal through formal methods, and it feels like more of like a gradient than it is like these defined buckets. So the idea of like, okay, well, I wrote down what the software should do, and I wrote a bunch of tests, running on like data. Like that feels like something that is like spiritually aligned with formal methods, just maybe at like a very, very shallow part of the gradient curve. And this happens a lot, in like the Rust language, where like there's kind of this spiritual question of like, okay, what is this language? Is it the compiler? Is it a specification? Is it a test suite? So like, is there a way to kind of like make that gradient feel a little bit more gradual, where a customer who has maybe some of these things in varying degrees of formality, you can kind of say, okay, well, you're starting here, and we can start to like work your way up into something more formal?
Yeah, I think that's sort of my hope for the things that I think that part of what this talk is sort of, trying to encourage people to work more in those kind of areas. Like if you have like a way of writing things down that could be turned into like a test suite automatically, this is very attractive. Or like if you have a way to sort of say, well, here's a sort of interface that I could kind of write down in a precise way, and then everyone can commit to it. Well, you're starting to get to the point where you're doing something useful. And I think that the key question is just like you say, like how is this useful like today, right? So in the Rust world, you have a test suite. If the test suite doesn't agree with what the compiler does, then it's just going to be rejected. So part of this is like the social process of kind of actually coming to agreements about this, which is difficult, I think. So yeah, I think that, but that's where I think the real opportunities here.
Another area that lots of committees around the world are discussing is AI ethics. How do you, if you have a search system, how do you know that you should believe it?
Yeah, I think that, well, you're preempting the very end of this talk where I have some rambling about AI, so maybe I'll save that question until the end. So I wanted to tell this anecdote because we did this project called Safe Docs, and we formalized PDF. And like, I think PDF's interesting because PDF's are used for all sorts of crazy things. Like, did you know you could embed a video in a PDF? I didn't know that. You can also embed JavaScript in a PDF for, reasons. You can also, like PDF also has, basically it's a sort of garbage collected format. So you can it's got like a kind of table at the end that says where all the valid objects are. And then you can write another table at the end which says that some of those objects are invalid, and then you can overwrite those objects. Anyway, it's really kind of fun format. There's a lot of crazy things. But we did this formalization of it, and to our sort of slight disgust, realized that, like, well, this is the picture you have. You have the standard, which is like the thing that it claims to do, and then none of the parsers do that. It's just like, it's for sort of somewhat good reason, because if you get a PDF and your kind of parser does, refuses to read it, you're probably not going to say, oh, well, this was a bad PDF. What you're going to say is, Apple's PDF parser sucks, right? And so the PDF parsers all do all this kind of crazy fix-up stuff for like ill-formed PDFs, but they all do it sort of a bit differently. And so that means that you have like, this kind of like, this sort of like, we live in this sort of slightly odd postmodern world where there's like a core of things that are well-formed PDFs according to the standard, and there's this kind of fuzzy boundary of things that could be PDFs if we look at them the right way. And then we have things that are a bit less a PDF, and then we have things that are definitely not PDFs. And there's just like, so you have this kind of totally bizarre world where like there really is not a discrete category of things that are files that are PDFs, and that you can reasonably kind of demarcate. Anyway, so this means we sometimes have this kind of conversation, like, so I sort of say, do you have a specification for your system? And they say, well, here's my 2-slide PowerPoint deck for the 100,000 lines of code. Or they say, here's a 7,000-line paper document written in semi-structured prose. And then we have this conversation where I say, oh, it sounds like your spec says your system does X, but your system actually does Y. And then they sort of say things like, oh yeah, that doesn't matter. Or they say, oh yeah, we changed that 6 years ago, or 6 months ago. And then you have this conversation like, I don't know, 400,000 times. And it's very sort of like, it's very hard to kind of come to an agreement about like exactly what the thing should do, because mostly people don't need to kind of have that level of knowledge about their own systems. And it's hard to formalize all the edge cases. It's very, very difficult, I think.
In that previous conversation, that's still a productive conversation, that is discovery of what does and doesn't matter, and the specification gets updated?
Yeah, it is. It's just, does this conversation kind of converge is the question. And like, I think sometimes you have an even worse kind of version of this conversation where you like say, hey, your specification says you can do X, and then, but the system does Y, and then the person says, I don't know whether that matters.
Which again seems really productive, right? Like, or as a potential priority.
Maybe. I mean, it feels like, again, like it is good from the sort of like, Platonic crystalline world of kind of like coming up with kind of correct specifications. But if you're working with a client, you only probably have a limited amount of bandwidth with them. And so they may not. And so if what you say is like, well, we can build a formal specification for you, but I will need sort of 160 hours with your best engineers, like working through the spec. And at the end, we'll have something which may or may not be related to the thing you actually want. That's just not very compelling, right? So it's really hard to kind of, like, again, this sort of comes down to like, what value are they getting from like this process?
Yeah, I think there is something missing for me here about the model of your clients, because to me, this would be the most valuable thing you get is this dialogue. And so it's interesting to hear something different.
I mean, I think one thing that I've sort of come to feel is that like, well, I haven't come to feel this, I knew this already, but I'm a huge weirdo, right? And one way that I am a huge weirdo is that I really care about precise definitions. And I think that when I'm working with clients, often I think sort of software engineers in practice, systems are sort of more grown than they are designed. And that means that they have a sort of core where they have a sort of well-defined behavior and everything, and then they have a sort of, like with PDF, you have a sort of fuzzy boundary around the edges. And this sort of offends me as a kind of formalist a bit. And I'm like, I would like the world to be neat and tidy. But it means that like there are sort of regions of sort of here be dragons where they just don't care that much what happens there. And it's very hard to kind of pin them down. So I sort of don't know what to do about that. It's sort of like, it feels like a bit kind of like epistemically threatening to kind of my whole way of thinking about the world, if that makes sense. Yeah, go ahead.
How often, I guess, in these conversations with a client, do you find that the impasse that they have found themselves to be at is that English or whatever natural language they're using is just not a sufficiently formal or precise specification level language, and they are either have massive gaps in their definition of their system, or their definition has grown to be a 7,000-page PDF, and they just keep on trying to like put more English into it to try to like specify it more closely, but that's just not what human languages are designed to do. And caveat, this is like a moderately leading question, because I think in the LLM era, there are a lot of people who are trying to use English and prompts to specify everything about wildly complicated systems, and I feel like we've already failed at that in many industries, and we've had to develop things like formal methods.
Yeah, and I think that's right. And often people do have like somewhat formal things. Like, I mean, a test suite is like a formal thing in some sense. Or you might have an architecture diagram. Like, a big part of the problem is like that these are often sort of slightly out of sync with the real system. Like the test suites are good because you can really tell whether or not they're correct or not. But like an architecture diagram is really tricky. Like, unless you're very rigorous, then it's hard to kind of keep them in sync. But you're right. I think that like most teams kind of know that you know, in fact, in DoD, often you have very formal processes of like, you know, requirements engineering. It's just they're often written in human prose, and they're not quite sort of the process of making them completely formal. Sort of a bit like kind of if you go to math people and say, hey, good news, you can use Lean to write your proofs. Well, they're like, oh, well, this requires a level of detail they really don't want, right?
Yeah, there's only so far that saying shall and thus will get you in formalizing.
Right,
language.
right. And yeah, I mean, I think that all that is totally correct, and I'm very optimistic about like LLMs as a kind of like formalism plus formalism as a way to communicate with LLMs. It seems like a very promising area to me for exactly that reason. Okay, I'm going to sort of speed through so I think there's like, I don't know, this might be too inside baseball, but like sometimes when people like talk about why people don't use formal methods, they're like, oh, well, all the tools suck very badly. And this is correct. The tools do suck very badly. But I don't think this is a good reason. This is the reason why people don't use them. So the theory is, oh, formal methods tools have bad usability, the documentation sucks, the interfaces are terrible, all this kind of stuff. And their other argument is usability is the dominant reason formal methods tools are not used. And so therefore, if we made the formal methods tools more usable, they'll be used a lot more. So I sort of agree with H1. I disagree with H2. I think that H2 is not correct. So I think that one thing to observe is that tools with poor usability are used quite a lot. Unix and Linux and AI LLMs and GDB and Haskell, sorry everyone. And the reason is these tools are like beneficial. They're very obviously beneficial and very obvious to kind of like see ways. When you use them, you can use them to sort of solve tasks. And so I think that like a good way of thinking about this is that if a tool has poor usability, it will be used for things by some people because it's beneficial. And engineers will use tools that suck if they are getting the benefit from them. And so what matters is, can the organization achieve a sort of proportionate or a benefit at proportional cost, right? So I think that it's a totally fine sort of thing to say that all these formal methods tools have sort of terrible usability. And that sort of like is a cost on the use of these tools. And we can sort of make the tool projects holistically a bit cheaper by kind of making the usability better. But it doesn't necessarily, may not move you into the region of kind of like being actually worthwhile, because it doesn't really increase how much benefit you get from them. And so if you're not getting the benefit you need, then the cost doesn't matter that much, right? This is my view of things. Okay, so these are my super hot takes. I also have some waffle about AI I could talk about, but this is kind of the core of the talk. So I can also just stop here if you'd like to. Yeah, go ahead.
I'm interested in these conversations about specification and overall. So I hear that one is that there's some sort of gradual formality that is introduced over time in a good pace. Another is there's acknowledgement that there is uncertainty or non-agreement or some unspecified behavior outside the core scope. And another part I hear is that it's a very social process, and that managing that agreement is actually very even articulating something to be agreed upon in a clear way is difficult. What would an ideal process? I don't know whether that covers the spectrum of things you talked about, but if you're thinking about tools or sort of social processes and enabled by tools that would make for specification, I don't know, more beneficial, more usable, or whatever, do you have like a specification of that?
Yeah, that's a great question. I think that like, so in one way, people use too many different ways of specifying things, and it's hard to keep them all in sync. And it's sort of formal specification forces you to be too precise. And so in a lot of ways, what you need is some way to like skip details where you need to, and you need ways to kind of I don't know, prototype at the specification level. But I mean, the really critical thing is it has to sort of be useful to you to actually do the specification task in some quite concrete way. So I said earlier, like, no one writes test cases. Well, it's not true, no one does, but like, not enough people write tests. And one reason is because a test doesn't help you until it kind of catches something. And so there's a sort of deferred benefits to writing to testing. And so I think that I think the critical thing is like, well, how could we kind of use specifications as a way to drive engineering as a sort of first-class thing rather than a sort of, I sort of think of this as like, how do we make testing, like specification, not like the thing that you do because you're eating your broccoli, right? It's not like a virtuous thing you're doing. How is it a useful thing to do, right? That's the kind of critical thing, I think.
I could imagine the specifications are like proofs. I could imagine just the types might be useful because the types are the handoff points. If I knew you were looking for an integer or a triple of integers, I could hand it to you. And then if I knew it had to be a Pythagorean triple, like I could just hand, where a squared plus b squared equals c squared, I could just hand it to you and like you check it if you want and not prove it.
Yeah.
And you could, like the types seem like good handoff points. Like I'm expecting something of this type or whatever. Are those, is formal methods also figuring out the types as opposed to the would that be more useful?
Yeah, I feel like the real successes for like mass adoption for formal methods, I mean, Rust is the obvious one. It's a very light kind of formal method in that, like MyPy or something like that, like sort of retrofitting, I think, properties onto existing bits of code at the type level so that you can say, hey, this function is supposed to this function has the following effect on memory, or this function always like produces Pythagorean kind of triangles or whatever. I think that's a really powerful idea that actually does give you benefit immediately and is sort of relatively easy to deal with. That's like sort of specification without proof. So like
typing and subtyping as available, but not requiring them to be specified all the way down to the subtype, all the way down to like the singleton subtype or whatever.
Well, and I think that you can sort of imagine a world where you kind of really drink the kind of dependent types Kool-Aid and you sort of say, I'm going to attach kind of types to lots of functions that say, the whatever property you care about your code, but then the problem for doing that is like, well, what do you do with those types? Then you have this kind of really high cost of like building the proof. So a big part of that is like, you've attached the types. How do you even kind of make sure that this code type checks according to this complicated type, right? So if your type is like, this function computes AES, right? Well, how are you going to kind of type check it? Well, you need to kind of write a proof, which is super expensive. Like if we could find a way to make proofs cheaper, that would be really valuable as well for exactly that reason.
But if you specified a super type of that, like you have this Pythagorean theorem, this triple is a squared plus b squared. If I just gave you an ABC triple and I don't check it for you, that's pretty cheap, right? I could just tell you, here's a triple. I promise you it's David certified to be a Pythagorean one, but I'm not proving that, and that's not in my type. And you just pull it in, and your code's going to get an error if it doesn't satisfy. But
right, I think. Well, you can write it down, but like a problem that people sometimes have is that they sort of say, okay, well, I'm going to like write a model of what my code does, but there's not going to be any connection to what the code actually does. And then what tends to happen is that there's this big effort to write the model, and then the code develops, but like there's no way to kind of keep the model in sync with the code. So you need some way to kind of, it's not always true, but it's often true that like unless there's some way of kind of using the spec in some sort of active way, then it tends to kind of drift away from, like ideally everything would be in CI. That's the real kind of the best case. So I think it's like a lot of this does again come down to just the cost of like the proof tasks, I think.
Something I'm picking up here in this conversation is when you had your sort of spectrum of sort of tools for software assurance, with types, where do types come into that? And so maybe type systems are a way of talking about some properties of your code, but not at the sort of precise level of formal specification, right? Yeah, David saying like you just have a type of a triple instead of a type of a triple with this particular property, right? And so that's some way that you can sort of not be over precise, but you can begin to specify expected aspects of your software and then you get compiler support and actually doing the checking and then live. I don't know. Is that in your spectrum? Do you
Yeah.
recognize that as formal methods, or?
Yeah, I mean, I think like as an on-ramp, sort of starting out, sort of, you have like untyped Python code, and then you sort of type it using MyPy.
Yeah.
Well, this is a very cheap and quite popular way to kind of like actually improve the reliability, and it's a kind of lightweight formal method in that sense. And I think that there's like a nice. This is, I think the gradual typing is a really great idea because it means that you can sort of pay as you go. So you can sort of say, oh, well, this bit of the code needs to be really reliable, and so I'm going to kind of insert kind of more like checking into it. And this bit of the code, it doesn't matter so much, or like we haven't got to it yet. So if you can do those sort of lightweight things, I think that's really valuable. And I think there's probably like, especially like AI-assisted, like sort of retrofit kind of efforts. I think it makes a lot of sense to think about like what could we attach to like as high-level specifications that look like types that we could then sort of like try and reify in ways that users can find useful. I think that sort of feels quite promising to me.
It feels like something you do in Rust now with like you define like a tuple struct for like an XYZ coordinate and one for like an RGB value, and they're the exact same data type, and you're not really formally proving any of that. You're just kind of like encoding your mental model of these types into your program, and then it will make sure that like it's not formal at all, but it's like kind of like maybe that's like the gradual thing you're talking about.
I think the only additional thing there is like Galois has some code bases where they do the sort of proverbial, turn on all the compiler extensions, it's sort of like dependently typed almost. And those bits of code are sort of notoriously hard to change because there are lots of, basically there's sort of morally a lot of proof obligations that when you make edits. And so that kind of cost is another kind of cost that really matters, like that sort of friction as you're kind of like, so ideally you would only specify at the interface which never changes, because change itself is really expensive if you have a lot of internal kind of like structure.
I guess it maybe related to what you just said last. I'm curious about, earlier we were talking about different sections of the code, and maybe some sections of the code matter more for formalizing than others. My sense is that often for projects, that's just the wrong sectioning or something. Like code sections have less to do with, like the thing that you want reliable is some sort of path over the code or something.
Yeah,
like that,
yeah.
Yeah, I don't know if.
Well, this is a.
There's also like Conway's law, right? Like which is that organizations and structure and the way your code sets up is actually at the boundaries, at the handoff points, as Dave was saying earlier. And so maybe it should work out that way. But somehow that feels quite related to what, and I'm curious to hear about it eventually from you, about how AI might end up doing it versus how humans tend to do it as a social process,
right.
Which might look quite different from the artifact itself or something like that.
Yeah, I think one thing you're just saying, I totally agree with, there's, like real software is sort of annoying in that like the abstraction boundaries don't often line up with the kinds of abstractions we would want. Like I think that parsing is a good example where there's a sort of idea of like, how you would structure a parser in, if you were kind of coming to it as an academic first principles project, but in practice, a lot of parsing code is sort of intermingled with the kind of like data processing logic that actually does the kind of deals with the data as it's coming in. And so this is, very annoying because it means that we don't have a nicely encapsulated parser somewhere where we can just sort of lift it out. I think that one area that I think is potentially really interesting is like getting the AI to try and do that sort of like, not even like kind of the typing of the code, like so specifying of the code, but even just sort of like trying to kind of like come up with sort of logical slices of the code which have a particular thing and then sort of say, I can do this refactor because I know that I'm not going to break anything when I make this edit, even though the code is sort of intermingled. That seems really powerful if we could do it.
Are there any formal specification systems that are kind of attempting to also be able to either act as or generate like lower fidelity documentation as well? I think like one of often the problems is like you have the architecture diagram you have the 6-slide PowerPoint deck, and those are not sufficient, but they are useful in a lot of other contexts. And so then you go in and say, well, we should do something formal, and it's like the XKCD standards, thing of like, okay, let's add another one of those. And I think, like when I look at like Lean, I'm like, okay, I can see the value here, but I'm also not gonna like throw that up on like that screen to like explain how the software is put together. Like, are there any systems that you can kind of, I don't know, maybe like downstream generate or?
Yeah, I think there've been a few of them. I mean, I think that this is another area that maybe AI is going to make a big difference too, because, historically kind of, you can turn a formal spec into a sort of very tedious kind of description, but it's not very easy to kind of like abstract to the level a human can kind of understand it. And there are other things like, which look more like just sort of like docstring type things, where you sort of have like alliterate specs where, you have like the spec and the kind of description and the code sort of live together in some sense, and you can kind of come up with projections of it. But yeah, I mean, I think that, your Lean spec is probably not the thing you want your engineers to be working with. And so ideally you'd want some way of like mapping between the different sorts of descriptions that you have in some sort of like, I don't know, both like transparent but also highly precise and nuance preserving sort of a way. Also, I would like a pony and, like a cherry on the top, and but those things seem they fight against each other, but they seem like that's kind of what you would want, really.
I think Cargo is pretty good at like the amount of documentation it can generate from just your like function signatures, basically. Like that's surprisingly good.
Yeah, I mean those things are great. Those things are really useful. Yeah, go ahead.
Could formal systems help in comparing, formal methods help in comparing systems? If they're formally specified, then you could say, is system B better than system A in certain respects, once you have formalization?
Yeah, I think that there's a, I think people sometimes talk about like software understanding. So there's like specifying in the sense of like you'd specify the thing and then build it. And there's also sort of like you have the thing and then you like lift a specification out of it. And you sort of say, okay, well, does system A have like some problem that system B doesn't have? I think that you can do that, but it is sort of like, as of today, incredibly hard to do because just lifting the spec out is just really expensive. So this is another area where maybe if we had like super powerful AIs, we could just sort of do that, and then we can use the spec in a useful way. But today it's hard to justify that as a use case because people, it's just doing the specification itself is really hard.
Well, I had a discussion today with friends in Europe, in England, about comparing automated proof systems because they have many different aspects, and so the question is which to choose for what you want to do. So.
I also have hot takes on that, but like that's a sort of separate question. I'm going to very briefly just sort of like, because I drew a nice diagram, I'm going to sort of be like, oh, what about AI? Come on, guys, we're in the Bay Area. What about AI? Well, okay, very quickly. Like writing proofs, very arduous. We don't like doing it. Like typically, though, like there's an interesting thing about the way that we do these proofs. This is like an interactive theorem proving architecture. So you have like a proof script and a world model, and then you sort of say whether your thing is actually verified. Well, how do you come up with the proof script? Well, traditionally, what you would have is a PSMGS cluster, proof searched by miserable graduate students, and then you would have and then you would sort of like figure out the proof script that way. The interesting thing here, though, is that this is sort of like an trusted divide here. So on the left-hand side, you don't care about the proof script, you just got to find one, right? On the right-hand side, you do care about your proof checker, but it can be kind of small. Well, the nice thing is this is just a search process, right? You're getting your graduate students to kind of like do your search process for you. And your checking process can be small and deterministic and easy to audit. This feels like a really good like candidate for AI because like you're really using your AI to kind of come up with that. It doesn't matter whether you trust your AI because your AI is just doing your search process. Once you have the proof script, you just feed it to Lean and Lean says yes or no. And if it says no, then you go back and say, kind of, give me another one, right? So I feel quite optimistic about at least some parts of AI helping some parts of formal methods, because like a lot of the cost here is this search for kind of proof candidates. And if we have like fancy AIs, maybe we can kind of like come up with these proofs very much more easily. This is sort of, I drew this diagram about 9 months ago, and at that point it was less obvious, but now I think it's so obvious it's almost not worth saying, but it is kind of now, I think, becoming more obvious that this is correct. Yeah, this would be very nice, because then maybe we could kind of like lift these kind of like circle of out of the kind of region of doom into the sort of region of happiness. This would be very good, and it feels kind of like somewhat like this might be about to happen, at least for some kinds of formal methods. I feel kind of quite bullish about the results we're getting in AI-assisted mathematics, like really making a big difference, and these technologies being much cheaper, and therefore they kind of, the cost benefit improves because they're in the region where we can actually use them. So I'm hopeful about this, and I hope that it's, we'll see what happens next, but I think that indicators over the last 6 months or so have been quite positive that this is in fact the world we live in. Blah, blah, blah. Okay, yeah, that's everything I have.